Well, welcome to our journey into complex analysis, and we're going to finish up with a couple of interesting results on terms of counting zeros and counting numbers of poles, and then we're going to use that to prove some rather interesting and important theorems. So in what follows, we're going to suppose that f of z is analytic in some domain omega, and that D is some domain contained in omega. And finally, for the moment, I'm going to suppose that f has only one zero at z equals alpha of order k in D. That means we can write our f of z as z minus a to the k times some function phi of z, where phi of a is not zero. So we've factored out all of the z minus a's out of my f, and I've got an analytic function here which is not zero at a. Now what we're going to be doing, we're going to look at the so-called logarithmic derivative of this. So I'm going to differentiate this using the product rule. So that's all I'm doing there. And then I'm going to divide by f of z. So this is the so-called logarithmic derivative, because of course the integral of that is the log of f of z. Now when you do all that and simplify, you get phi dashed over phi plus k on z minus a. Now phi of a is not zero, and that means that this function here, phi, is analytic, and this function then is going to be analytic in D. And so I'm going to choose gamma to be the boundary of my domain D and integrate around it. So I'm going to integrate both sides and divide by around gamma, and divide by usual 2 pi I. And when you do that, this integral here is just going to be, well, the integral of this around gamma is 2 pi I k, and when I divide by the 2 pi I just get k. So this integral then pulls out for me this number k, which is the multiplicity of the zero. Now we use our usual argument. If we've got more than one zero, we can isolate each of these zeros. And usual argument, we see that if f is analytic in D and gamma is the boundary of D, then this integral, 1 over 2 pi I, of the integral of the logarithmic derivative is just equal to n, where n is the number of zeros counting multiplicity. Number of zeros counting multiplicity. Simple example, very trivial example really. If we take f of z to be z to the 10, then this thing here has a zero of order 10. So there are 10 zeros of this counting multiplicity, and if I just work out this integral, the 1 over 2 pi I of the logarithmic derivative of this around the unit circle, then we simply get this, and that's going to be 10 times the integral of 1 over z. The integral of 1 over z is 2 pi I on the unit circle, so divide by the 2 pi I just spits out to 10 as expected. Well, that was rather nice, so we now turn our attention from zeros to poles and see what happens there. So I'm going to suppose now that f has a pole of order p at z equals a in D, but no zeros or other poles there. So just one pole of order p. That means, again, I can write my function as psi of z over z minus a to the p, where psi of a is not zero. In this case, again, we can work out the logarithmic derivative, and it just turns out to be this. It's the exact same calculations as we did above almost, except we had this in the denominator. And now we get a minus here, which is nice. Again, we take gamma to be the boundary of D, and we integrate the logarithmic derivative around that contour, divide by 2 pi I. So this is analytic, this disappears. This one here again gives me 2 pi I times minus p, and divide by 2 pi I gives me the minus p. Now we do the same idea as before. If f is analytic except at finitely many poles, and there are no zeros there, and gamma is the boundary of D, then this integral is going to give me minus p, where p now is the number of poles counting the order of the poles. So number of poles counting order. Now we can put that together and we come up with the following lovely result. if f is analytic in some domain D except at finitely many poles, then we have the 1 over 2 pi I of the logarithmic derivative of f along some contour which is the boundary of D as before. This is equal to n minus p, where n is the number of zeros counting multiplicity and p is the number of poles counting, well, not multiplicity but perhaps counting order, I should say here. Would be better to say. So for example, if I've got this function here, z to the fifth on z minus 2 squared, then this has a 0 at z is 0 of order 5, and we've got a pole of order 2 at z is 2, and so we can predict that the integral around this contour, which contains both of those, zeros and poles, is going to be the number of zeros, which is 5, minus the number of poles counting order, that's 5 minus 2, times 2 pi I is 6 pi I. Now, this is a nice little theoretical result, but in fact it's got some rather interesting implications, in fact, quite a number of them, and the first one of the implications is this beautiful Rouches theorem, which is used to find the number of zeros of certain functions. So if f and g are analytic inside and on a simple closed curve C, now if the modulus of g is less than the modulus of f for all points z inside the contour, then f plus g and f have the same number of zeros inside C. So you can see one interesting application of this is if you start off with some function f, some function, and you can split it into two functions, f plus g, and you've got some control on how many zeros there are inside f, then that will give you information about how many zeros there are of the thing you started with, the f plus g. We'll have a look at an example in a moment, just to do the proof of this. So I'm going to put capital F to be g over f, so g is little f times capital F, and n1 and n2 are the number of zeros inside C of f plus g and f respectively, and we want to show the number of zeros of this equals the number of zeros of this. So using our result we had before, n1 then is going to be 1 over 2 pi I times the logarithmic derivative of f plus g around C, and n2 is going to be that expression for f. And we're going to subtract these two because I want to prove that this thing here is in fact 0, so the number of zeros of each are the same. So I can bring these two together, and I'm going to leave this one alone for the moment, and I'm replacing the g dashed with f dashed. I have to differentiate capital F times little f. So the g dashed by the product rule is going to be little f dashed capital F plus little f capital F dashed. I can now split this into two bits. I can take this one over that, and then the f's cancel, the small f's cancel, and if I take this one divided by that, I can factor out a capital F dashed on the top, sorry, a little f dashed on the top, little f on the bottom, and I get a 1 plus f factor cancels out, and I just get this. These then cancel out nicely, so the integral, this difference turns out to be just this thing. And this one here is looking like I want to expand this out as a geometric series. And we can do that because since little g is less than, in modulus, is less than the modulus of little f, that means the modulus of capital F is less than 1. And that means this is a valid expansion here. And now I can just integrate term by term. So each one of these you can integrate term by term. They're all analytic around a closed contour. This integral is going to end up being 0. And that will then mean that n1 and n2 are equal. simple, nice example of that applied to a polynomial. So we want to prove that the zeros of that lie of this polynomial z to the 7th minus 5z cubed plus 12. These lie in between the two circles mod z is 1 and mod z is 2. So it's got 7 roots, and we want to show they all lie in this annulus between the two. Now what you do with this, firstly I want to show that they all lie inside the big circle, mod z is 2. So if I want to show they all lie inside this one, then I need to get something that I can easily write down has 7 zeros, and obviously that's z to the 7. So I'm going to take my f of z to be z to the 7, because I can easily see how many zeros there are inside mod z is 2, and then g of z is what's left. And we hope then we can show that mod g is less than mod f. So as I mentioned, this one is obviously has 7 zeros inside mod z is 2, counting multiplicities. And for z on the circle, the modulus of g is, using the triangle inequality, is less or equal to that. And if I'm on the circle mod z is 2, then 2 cubed is 8 5s are 40, plus that's 52. On the other hand, on that circle mod z equals 2, if the modulus of f of z is 2 to the 7th, which is 128, and 52 is less than 128. So we've satisfied the conditions of Rouche that mod g is less than mod f for all points on the contour, and that means this function and the sum of these, which is the polynomial I started with, have the same number of zeros inside mod z is 2. i.e. namely 7 inside that circle. So we've now got to show there are no zeros inside the smaller circle mod z is 1, so that they lie in between. So I want a function that I know has got no zeros, so I'm going to pick the constant term, because the constant is not 0. So now I'm going to put f of z to be 12, and then my g of z is what's left over. Then f clearly has no roots inside mod z is 1, and if I'm on that circle, then the modulus of g is the modulus of this. Triangle inequality says this is less than 6 for mod z is 1. And that's certainly less than 12, which is the modulus of g of z. And that means that the polynomial I started with, this one, has no zeros, has the same number of zeros as this one, i.e. none, inside the disk mod z is 1, and that means they all lie in between. Little challenge problem to play with. We want to prove the equation. This works not just for polynomials, but we can do this for all sorts of things. So you want to prove this equation, z plus 3 plus 2e to the z equals 0, has precisely one root in the left-hand plane. You need to think a little bit about how you're going to deal with the left-hand plane. Probably one should look at a semicircle. Okay, so out of this also we get yet another proof of the fundamental theorem of algebra, which is rather nice. So here's another proof that can be derived from Rouches theorem, fairly easily in fact. So again, we start off with there's our polynomial, and we're going to assume the a(n) is not 0, of course. And I want to prove, in fact, this is the fundamental theorem of algebra says there's at least one root inside here. This is slightly stronger. It says that every polynomial of degree n over c has exactly n zeros in C. So once again, you pick the bit that you know has got exactly n zeros. So I'll just take the first term here. So f of z is anz to the n, and g of z is what's left. So I take the polynomial minus this first term. And we're going to let C now be a circle of radius r bigger than 1, centre the origin. Then it's obvious that this function f has exactly n zeros, counting multiplicity, inside C. And now I want to show that mod g is less than mod f. So I'm going to look at the quotient of these two. the modulus of that, which is just the modulus of g divided by the modulus of f. Now these ANs, these are complex numbers in general, so this is using the triangle inequality. This is less or equal to, and we're on the circle mod z is r. This is mod a naught plus mod a 1r plus and so on. Now r is bigger than 1, so I can say each one of these is less than this one. So I can say less or equal to this with r to the n minus 1s all the way along. And most of the r's cancel, but I'm still left with 1 in the denominator. Now these are all constants, so the top is some bounded constant, but the r I've got some control over, so I can choose r large enough to make this expression less than 1. And that means for sufficiently large r, then mod g over mod f is less than 1. And in particular, on that boundary circle, the mod g is less than mod f on the boundary circle. And that's it, because then we can conclude that f g plus f, which is the polynomial we started with, has the same number of roots of f, i.e. exactly n in the complex plane. Little corollary to that, you might like to, I won't do a proof of this, but it follows immediately from that, is if you've got this polynomial with a n not naught, then p has all its zeros inside a disk radius this thing. And in fact, I got that follows immediately from what we did up here. So we actually get some bound on where all the zeros, on how big a circle you need to take in order to guarantee that all the zeros are inside that circle. How good this bound is another question, but certainly within this bound all the zeros occur. And that's the end of that little section, and we have one more to go to finish off this chapter.